Hi, my name is Joy Jones and I'm in Physics 2212, section Q04, taught by Dr. Ed Greco, and this is my Physics Extra Credit video assignment. Thanks for watching. So I went to 2 lectures this semester and they're both related to sports, but I think I'm only going to have time to review one, so I'm going to choose the one that I like the best. And that was actually the one that was held on Thursday, April 4th, 2013. And that was held by Alan M. Nathan, and it was titled Baseball and Physics. You can observe a lot by watching. And as a side note, if you want to know more about Mr. Nathan and his research, you can go to baseball.physics.illinois.edu. So probably the most important topic that he talked about was the batted ball speed. And that is basically this equation. And so what determines the batted ball speed? Well, first is the pitch speed and the bat speed. So you have the collision efficiency, and that's the property of the ball and bat, and that's denoted by Q. So batted ball speed, BBS, is equal to Q times the velocity of the pitch plus 1 plus Q times the velocity of the bat. So typical numbers of this, you would have a collision efficiency of Q equal to 0.2, so your 1 plus Q would equal 1.2, and so that would give you 85 plus 70, which would give you 101 miles per hour, which translates to about 400 feet. So one thing to know is that the velocities of the bat and the pitch are not equal. So the velocity of the bat matters much more than the velocity of the pitch, and this is proven by the fact that each mile per hour of bat speed translates to about 6 feet, whereas each mile per hour of the pitch speed translates to about only 1 foot. And the collision efficiency is also dependent upon the weight of the bat, and the bat speed is also dependent upon the weight of the bat or the moment of inertia, so how heavy it is. Then there's vibrations in the sweet spot. So just like tennis rackets have sweet spots or best spots, the baseball bats also have that. If you don't hit the baseball at the bat's sweet spot, then there's lots of vibrations, and it basically vibrates in the batter's hands, which doesn't translate very well as far as speed or distance. So, but if you do hit the ball in the bat's sweet spot, then there's hardly any vibration at all, and it's a very good swing and it has good batted ball speed and distance. If a batter drops the bat like the instant before the ball hits the bat, does it have the same effect as if he were to swing the bat all the way through? And actually the answer is it's the same. And he showed a video of slow-mo, and you could actually see the batter instantly let go of the bat, and the bat swings on through, hits the ball, and it does have the same effect. So that was really cool that he proved that, and I believe the batter that did that, if you want to look up the video, is Tom Frazier. And so the second thing, the big question is, why is aluminum baseball bats better than wood bats? And the answer is the weight distribution. There's a lower moment of inertia, and so it's swung faster, so there's a lower collision efficiency, that Q that I showed you in the equation earlier. So there's a higher bat speed and the lower Q. He next mentioned Tim Wakefield, who's a very famous pitcher, and he's famous for throwing knuckleballs. And knuckleball movements are completely unpredictable by both the batter and the catcher, because they may look like they're going over here, but then they'll go over there. And you can test this by wind tunnel data, high-speed video, and even tracking data. But yeah, it's completely unpredictable, which is why pitchers who throw effective or very efficient at throwing knuckleballs are very successful. And I'm going to mention another one, R.A. Dickey, and later in my video that I found out from later research. Okay, and quickly wrapping up, there are 3 things that you can do to affect the home run distance, and one of those is the air distance. So for example, in San Francisco, the ball is going to travel farther than in Denver, where it would travel a lower distance, and that's again due to the air density. And also temperature. So the higher in temperature you go, the faster the ball is going to travel. And that's the equation is about 2.5 feet per 10 degrees in Fahrenheit. I went to the 60 Minutes website and looking for the video that Dr. Ed Greco said that they were filming there. Unfortunately, I didn't find one that had video of the lecture that I attended, but I did find one. It's from the April 14th episode, and it's titled "The Knuckleballer R.A. Dickey Finds His Perfect Pitch." And he's a pitcher that was recently traded from the New York Mets to the Toronto Blue Jays. And basically, he's a fantastic knuckleballer. And so why is the knuckleball called the knuckleball? It's actually called that because whenever you pitch it, the catcher only sees your knuckles. And it's basically thrown with your fingernails, actually. And remember, that's the one where it only has 1.5 revolutions from the time it leaves the pitcher's hand to the home plate. Again, thanks for watching. I know this is long, but I hope you enjoyed it. Thank you.